Okay, so looks like we're about to go live. Okay, so now we are live. So I must apologize. Let me start off with that because I did not realize until about Friday or Thursday, I don't remember when, that I did not post the videos for the thermodynamics chapter. I started off with it on Thursday and I was supposed to post it, but I didn't realize that I didn't. So what I'm going to do, it won't affect us very much because this chapter is a relatively short chapter. So I'm just going to go through, certain topics in this chapter. And at the same time, we will refer to the assignment for this chapter, which is assignment 6, so that we can answer questions based on what we have covered so far. Now, if I recall, and please correct me if I'm wrong, the last thing we talked about was, let me see here, the second law of thermodynamics, right?
Yes, sir.
Okay, good. So what I'm going to do now is go to assignment 6 here. And we, based on what we have covered so far, should be able to answer questions 1 and let me see here, 2 and 3. Oh, maybe just, I'm sorry, just 1 actually, because let me go back to this here. Because, okay. I don't think, did we do this example? I'm trying to remember. Does this look somewhat familiar to you guys from last class?
I believe we did this one.
Huh?
I think we did this.
Okay, all right. That means that we should be able to do more questions. All right. Well, okay, tell you what, just to be on the safe side, let me just briefly go over the change in entropy. So just to backtrack a bit, entropy, we said, is basically a measure of the degree of disorder of a system, all right? And what that means basically is that the greater the level of disorder, the more disorder the system, I'm sorry, the greater the entropy of the system, the more disorder the system is, all right? And therefore we made comparisons between, like, for example, the same substance. If you have a solid or a gas, the gas would have a greater entropy compared to the solid, for example, all right? And we can actually measure this value, and we can actually measure what is called the standard entropy of a reaction or the standard entropy of a system. And basically that will be the entropy that is measured under these conditions, standard temperature and pressure, where the standard temperature is 25 degrees Celsius and the standard pressure is 1 atmosphere, all right? And of course, we represent the fact that it's measured under standard conditions with this small o as the superscript, all right? So if you have this reaction, hypothetical reaction, then the change in entropy would basically be the sum of the entropy of the products minus the sum of the entropies of the reactants. Of course, you have to take into account the coefficients. And these values can be identified in tables for different substances, such as in this example here. So in this particular case, you take the total entropy of the carbon dioxide minus the total sum of the entropies of the carbon monoxide and oxygen. And these are the values that you can get from the tables. And I think I pointed out where the tables are. If you need me to point it out, I'll show you again. So all you have to do now is plug these numbers into the equation. As you can see here, this part here represents the total entropy of the product, which is carbon dioxide. You multiply that by 2 to get the value for carbon dioxide, and then you subtract from that the total entropy of the reactants, which is 2 times the entropy of carbon monoxide plus the entropy of oxygen. And we plug these numbers into this equation, and you're going to get the entropy of the reaction under standard conditions, all right? So that's basically how that is done. And as you can see, this is kind of similar to what you would have done in General Chemistry 1 when it comes to calculating the enthalpy of a reaction, where you use the values given in the tables and you plug them into the equation similar to this one, taking into account the coefficients, and you get, when you do your number crunching, you get your final answer. So it's very similar when it comes to calculating the enthalpy change of, the entropy change of a reaction, very similar to how you would approach calculating the enthalpy change of a reaction. Okay, so with all that said, let me get out of this here, and now I'm going to move on to the assignment, starting with question number 1. And for question number 1, I think by now you should be able to handle this. So the question says, in each of the following pairs of compounds, circle the one you'd expect to have the higher entropy. And in the case of A, they gave you hydrogen sulfide liquid and hydrogen sulfide gas. So which one would you expect to have the greater entropy?
The gas.
The gas, exactly. What about B, sodium gas and sodium solid?
The gas. The gas again.
Mm-hmm. What about C, H2O gas at 150 degrees and H2O gas at 200 degrees Celsius?
The one at
what?
The one at 200.
Or 200, exactly. And then the final one, sugar as a solid and sugar dissolved in a cup of water.
The dissolved sugar.
Exactly. Okay, very good. So that's basically how you can quantitatively tell which one has a higher entropy value. Now, for this one here, and I'll probably just do one and leave the others for you to try on your own. It says, using the tables provided in Canvas, calculate the entropy change for each of the following changes, all right? And like I said, I don't remember if I told you where in Canvas you can find it, but let me just show you briefly. So you go to Files, and then you go to Tables. Where is it? Okay, Tables. And then where it says, where is it? Thermodynamic data. That's the one. All right. Okay, so this is the table that you'll be using. And again, you'll have access to this table in your future exams, tests, whatever, right? And just to explain this table briefly. So to the extreme left, you'll have the different substances, and make sure that you pay attention to the state symbols, because of course, the state affects the value of the enthalpy, entropy, whatever, right? The column next to it gives you the enthalpy values. And if you have had me in Chem 1 last semester, this is what you were using when we were looking at thermochemistry in General Chemistry 1, right? And then over here is what we were just talking about, entropy. So these are the entropy values for the substances over here. So for the questions that we're about to do, this is the part that you would be looking at in order to get information so that you can do the appropriate calculations, all right? Okay, so with that out of the way, let's talk about, what am I doing? Go back to this. Let's talk about the questions for number 2, all right. A, so it says here you have to calculate delta S for the conversion of graphite to diamond. So the way I would do that is, of course, I would consult the tables to see what the entropy values of graphite and diamond are. So when I looked this up, what I found, because I did these problems already, let me go to my writing thing here. Okay, so in the case of graphite, when I looked it up, graphite has a value of minus 5.740 joules. And diamond had, oh, by the way, this is joules per mole Kelvin, all right? And then diamond has a value of 2.377 joules per mole Kelvin, all right? So basically what you have to do to find delta S standard, that would be equal to the entropy of the product, which is 2.377 joules per mole Kelvin minus 5.740 joules per mole Kelvin. And you work that out. And according to my calculations, this turns out to be equal to minus 3.363 joules per mole Kelvin. And that's basically it. All right. So very similar to what you would have done in the case of changing in entropy, in enthalpy, is very similar to what you would do in these cases where you're calculating the standard change in entropy.
Would it not be negative or minus negative 5.740, turning it into a positive?
No. In fact, the entropy value itself cannot be negative for a substance. So basically, it's 2.377 minus 5.740. So if you were to look up the value for the, okay, I understand why you asked that question. There shouldn't have been a minus sign here or nothing there.
Okay.
That's why you asked, right?
Yes. Yeah,
Right.
I was confused there.
Yeah, I'm sorry about that. But what you just asked provide me the opportunity to say that entropy cannot be negative, right? There's no such thing as a negative entropy value for a substance. Now, the change can be negative, but the actual value of entropy cannot be negative. All right? And that's pretty much the approach that you would take for all the other questions. Well, in this part anyway, let me see here. Okay, you know what? So let me move on to question number 2. You should try the rest of question number 1 on your own, but if you have any questions, feel free to call me about that. So what I'm going to do is clear this, and I'm going to do this problem here. And basically, it's asking for you to do the same thing. It's asking for you to calculate the entropy change for that equation. Oh, by the way, let me see here. Okay, you know what? Let me not say that. So in the case of question number 3, again, you'd have to go to the tables and look up the values for the entropy, the standard entropy of graphite, hydrogen, and propane, which is what this is, C3H8, right? So basically, when you look them up, you see that carbon in the form of graphite has a value of 5.740 joules per mole Kelvin. Hydrogen has a value of 130.68 joules per mole Kelvin. And propane over here has a value of 270.2 joules per mole Kelvin. All right. So to find delta S standard, that's a change in entropy, it would be the product value, which is 270.2 joules per mole Kelvin, minus the sum of the entropy of the reactants. Now, because you have a 3 here, you have to multiply this value here by 3. You're going to get 3 times 5.740 joules per mole Kelvin. And then we're going to add to that 4 times, because you have a coefficient of 4 here for the hydrogen. So that would be 4 times 130.68 joules per mole Kelvin. And then we simply do the number crunching. And when I did that, I got 269.7 joules per mole Kelvin. All right, this should be a 7. So that's basically how that is done. So again, very similar to the approach that you would take when it comes to calculating the change in entropy. I keep confusing the 2 terms. The change in enthalpy, you're going to take the same approach when it comes to calculating the change in entropy. Okay, any questions about that? Any questions? Any questions?
Yes, sorry, did you get a negative value for that number or was that positive?
You mean the final answer?
Yes.
Yeah, that should be positive. And again,
Okay.
if I've made any mistake, and that's why I keep saying to you guys, you know, even though I'm quite confident in my answer, I could be wrong. So make sure that you check after me, make sure that I'm doing the right thing. And feel free to correct me if I've made any error, all right? Okay, but yes, I'm fairly confident that the final answer should be a positive answer. All right.
I got a negative answer.
Oh, you got a negative? Okay,
Mm-hmm.
let me recheck this. I guess that just goes to show I'm not perfect. So let me, excuse me. So this is 3 times 5.740, and then I add that to 4. Hold on. Let me do this again. 3 times 5.740, and then you add that to 4 times 130.68, and then I subtract that from, yeah, this looks like it should be negative actually, 270.2. Okay, so you're right, this should be negative. All right, thank you for that. I really appreciate it. I really appreciate that. All right, excuse me. So the answer
Are
should be
significant figures important in this case?
yes. In this case here, based on my calculation, you'd have to round off your answer to 1 decimal place. And the reason why is because the lowest number of decimal places is here in terms of the numbers involved in the calculation. If you were to multiply 3 times that, you're going to have 2 decimal places here, I think, if I remember correctly, and the same here. So basically, you round off to 1 decimal place. So the answer is going to be minus 269.7. All right. Okay. If there are no more questions on this, let me clear this here and scroll down. And we're going to look at, oh, we can't do number 4 yet. So because there are some other things that we need to cover. So let me go back to the PowerPoint here and move on to the next topic. Well, actually, same topic. Let me see here. Okay, so these are just some general situations where we can basically predict whether or not the entropy is going to be positive or negative, just looking at the reaction, the products, and the state symbols, and so on. So the first statement here is that when gases are produced or consumed, if a reaction produces more gas molecules than it consumes, then the change in entropy will be greater than 0, right? And if the total number of gas molecules diminishes, then the reverse is true. The change in entropy will be less than 0, all right, which makes sense, all right? If you go from left to right of a reaction and more molecules are produced, as you go from left to right, greater disorder and therefore greater entropy. And the reverse would be true as well. However, if there's no net change in the total number of gas molecules, then delta S may be positive or negative. So in that kind of situation, you cannot really predict by looking at the equation. You have to actually do the calculations like the ones that we just did. One thing you can be sure of is that delta S standard will be a small number. So it may be small and positive or small and negative, all right? But the only way you can determine delta S if the number of moles of gases are the same on both sides is if you actually do the calculations. Otherwise, you can make a judgment, accurate judgment, as to whether or not delta S will be positive or negative. So for example, let's look at this question. This question is asking, what is the sign of the entropy change for the following reaction? And it gives you the equation. So what do you think the answer is?
Would it be a negative?
And why do you say that?
Because it looks like there's less moles produced.
Less moles of what? Of
Of
gas,
zinc.
right?
Yeah.
Exactly. You have 1 mole of gas on this side. You have 0 on this side. So basically, you can conclude that the number of moles of gas molecules will go down, and therefore delta S is negative. Okay, so let's talk about entropy changes in the surroundings as it relates to the system. So basically, if you have a reaction taking place here, right, and let's say it's exothermic, right, that means that heat will be transferred from here to the surroundings, right? Then the result of that is that the entropy of the surroundings would increase. So delta S of the surroundings will be greater than 0, all right? On the other hand, in the case of an endothermic reaction where heat is absorbed by the system from the surroundings, then the result is that delta S of the surroundings will be negative. So that's basically how the enthalpy change affects, whether or not a reaction is exothermic, affects the system or the environment in terms of increase or decrease in entropy. all right? Another thing I want to point out here is the third law of thermodynamics, all right? This is the third law of thermodynamics here. It says the entropy of a perfect crystalline substance is 0 when the absolute temperature is 0 as well, right? And that is demonstrated in this, in this graph right here, where we have entropy plotted on the y-axis, temperature on the x-axis. And basically, if you start from here, of course, this is a gas. As you lower the temperature, the entropy of the gas decreases, and then there's a big decrease at the boiling point, right? And then what happens next is that there's a gradual decrease as you lower the temperature of the liquid. As you lower the temperature of the liquid. And then when you get to the solid state, there's a significant decrease again in entropy. And then that entropy continues to fall as the temperature decreases until you get to the 0 part of the axis, of both axes. And that would represent a perfect crystal, basically. All right. So that's basically what the third law of thermodynamics is saying. It's saying basically is that if you cool the substance or cool a system to a sufficiently low temperature, such that the temperature is 0 Kelvin, then what you have is a perfect crystalline substance. And what that basically means is that the substance will, in terms of the particles, will have no energy whatsoever in terms of translational, rotational, or vibrational energy, right? So that's basically what the third law is saying. Okay, so now we're going to get to how do we actually predict whether or not a reaction is spontaneous. So just to remind you, a spontaneous reaction is one that basically occurs by itself unassisted, right? So no energy has to be supplied from the surroundings in order for that reaction to take place. Now, if you recall, we said that delta H, usually when a reaction is spontaneous, that usually means delta H would be negative. In other words, the reaction is exothermic, and delta S would be positive, which means that basically there's a corresponding increase in disorder. However, that is not true in all cases. There are some reactions, for example, that are spontaneous, but endothermic, and you have also some reactions that are spontaneous, and delta H would decrease. So we have to find a different way of determining whether or not a reaction is spontaneous. And people have looked into this, and Gibbs, this particular guy here, came up with an equation called the Gibbs free energy equation, which is given by this right here. And delta G here is a term which basically helps you to predict whether or not a particular reaction is spontaneous. And as you can see, delta G is a function of both delta H and delta S, the change in enthalpy of the system and the change in entropy of the system. And also temperature plays a role as well in this equation, right? Now, the actual definition of Gibbs free energy, it is the energy associated with a chemical reaction that can be used to do work, all right? So basically what they're saying is that the Gibbs free energy is the energy that can do work as a system undergoes its process. Because the delta H here would be the heat change that occurs, but part of it would be used to make changes to the entropy of the system. So basically what we're saying is that the free energy plus the energy that would result in a change in entropy would be equal to the enthalpy change of the system. And as stated here, delta G is basically the criteria that we use to determine the spontaneity of a reaction. So basically, this is how we use delta G to make such predictions. Delta G being negative, if that's the case, then the reaction will be spontaneous in the forward direction. If delta G is positive, that means that the reaction is not spontaneous in the forward direction. Instead, it's going to be spontaneous in the reverse direction. And then finally, if delta G is equal to 0, what that means is that the reaction is in a state of equilibrium, all right? So that's basically what we do, what we calculate in order to figure out whether or not a particular reaction is spontaneous. Obviously, we need to determine what delta H is for the system at the particular temperature and what delta S is as well, all right? So once you know these two terms, and if you know what the temperature is, you just plug the numbers into this equation, and that will give you delta G, which would be the free energy, which indicates whether or not the reaction is spontaneous based on what we have here. All right. So that leads us now to a discussion of what we call the standard free energy of reaction, delta G with a small o or 0 as a superscript. So that is a measured delta G value for a reaction under the standard conditions. Again, the standard conditions would be that the temperature is 25 degrees Celsius and the pressure of any gases involved would be 1 atmosphere, right? And again, it's a similar approach in terms of determining the delta G for reaction under standard conditions as we looked at in the case of change in entropy. Again, going back to the table that I showed you, let me see if I can find it here. The middle column, or I should say the third column from the left, is what gives you the free energy of formation for the different substances here. And one thing I want to point out here before I move back to the PowerPoint is that one thing that delta G values have in common with enthalpy values is that for the elements in their free state, the enthalpy of formation under standard conditions is always going to be 0. So as you can see here, for aluminum, it's 0 for delta G. Scrolling down, for arsenic, the gray form at least, it's 0. For barium, it's 0. So any element that is not combined with anything, any other element, you can automatically assume that its free energy of formation is equal to 0. All right. So going back to the PowerPoint here, and let me make this full screen. So if you have a hypothetical reaction as indicated here, again, we calculate delta G for the reaction in pretty much the same way that we would calculate the change in entropy, right? We take the sum of the enthalpy, or I should say the free energy of the products, and subtract from it the sum of the free energy of the reactants, all right? So that's basically how delta G would be calculated, right? Now, please note, the standard free energy of formation is the energy change that occurs when 1 mole of the compound is formed from its elements in their standard state. So this is, again, similar to what we would say about the standard enthalpy change, right? It's for the formation of 1 mole of the substance, all right? And as you said before, as I pointed out earlier, delta G formation for any element in its standard form or stable form is 0, all right? So that's basically some introductory comments concerning standard free energy calculation. So for example, let's say you're given this question, you're given this balanced equation, and you're asked, what is the standard free energy change for the following reaction? So as we would do in the case of calculating the change of entropy for a system, we go to the table and we look up the values, right? Now, of course, we have to set it up such that each of the free energy formation of the different elements under standard conditions will be multiplied by their respective coefficients. So that's why we have a 12 here, multiplied by the free energy of formation of carbon dioxide, plus 6 times the free energy of formation of water, minus 2 times the free energy of formation of C6H6. And you'll notice that oxygen is not included because we can basically assume that the free energy of formation of oxygen is 0. So therefore, they did not include it here. And then we just put the numbers in, which you would get from the table. And in this particular case, the free energy standard for change for this reaction works out to be equal to minus 6,405 kilojoules. So that's basically how that is done. So the next question is the reaction spontaneous at 25 degrees? Now, if you remember the rules that we mentioned before, if delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction, as it is written, is non-spontaneous. And if delta G is equal to 0, the reaction will be at equilibrium. So obviously, because this is negative, we can say that delta G, or I should say that the reaction is spontaneous as a result of that, all right? So that's basically how we would answer that question, all right? Okay, so any questions about this particular example? Any questions? Any questions? Okay, so just some final comments here concerning the relationship between delta H, delta S, T, and delta G, right? We can actually make some predictions based on the signs of delta H and delta S and the magnitude of T as to whether or not a reaction is spontaneous, all right? So what we're going to look at is different scenarios, starting with a situation where both delta H and delta S is positive, all right? So let's say delta H is positive and delta S is positive. So the question is, will this reaction be spontaneous? And the answer is it depends on the magnitude of the temperature, right? So if you think about it, if you think about the algebra of this equation, if delta H is positive and delta S is positive, and the temperature, let's say the temperature is very high, what that would mean is that this value here would turn out to be greater than this value here, right? So what that means is that if the temperature is high enough, very high, let's say, that means that delta G is negative, which means that the reaction is spontaneous. So that's what we're saying here. The reaction will be spontaneous at high temperatures, all right? On the other hand, if the temperature is low, so low that this term here is less than this term, what that means is that if you're subtracting this from a term that is higher, that means that delta G will be positive. And therefore, basically what that means is that the reaction is non-spontaneous. In fact, it will be spontaneous in the reverse direction. And a good example of this would be this reaction right here, where the decomposition of mercury oxide forms mercury in a liquid state, of course, and oxygen. Okay, so that's what happens if both delta H and delta S is positive. Now let's look at what happens if delta H is positive and delta S is negative, right? If that's the case, now if you think about it, if delta H is positive, right, and delta S is negative. If delta S is negative and you have a minus T here, that means that minus T times something negative is going to be positive, which means that delta G will be positive regardless of what the temperature is, all right? So as stated here, delta G is always positive, and what that means, obviously, based on what we discussed before, is that the reaction will be spontaneous in the reverse direction, all right, at all temperatures. Okay, so that's what happens if delta H is positive and delta S is negative. Now, if you were to reverse the signs here, where delta H is negative and delta H is positive, so if you think about it here, if delta H is negative and delta S is positive, then basically delta G will always be positive because you're going to have a negative value here, subtracting from that something which is positive. So that means that the answer is going to be always negative, which means that such reactions will always be spontaneous at all temperatures, all right? And then finally, if both delta H and delta S are negative, so if delta H is negative and delta S is positive, or I should say negative, again, this is one of those situations where it depends on the temperature, if it's high or low, all right? So in the case where the temperature is, let's say, high, right, and delta H is negative and delta S is negative, that means that the delta H value, I'm sorry, the delta G value will be, let me see here, hold on, at high temperatures. Right, delta G value will be positive. So therefore the reaction will be spontaneous in the reverse direction. On the other hand, if the temperature is low, what that means is that delta G is going to be negative, right? Because you're going to have something negative here, subtracting a small number here. So delta H will still be negative. So therefore, I'm sorry, delta G would still be negative. So therefore the reaction will be spontaneous in the forward direction. And an example of that would be this reaction between ammonia and hydrogen chloride to form ammonium chloride, all right? So this is just basically a summary of how the different factors will affect the sign of delta G and therefore whether or not the reaction will be spontaneous. Okay, another thing I want to mention before we move on to the next assignment question is the relationship between delta G and chemical equilibrium. And it turns out that there's a reaction between the free energy of a reaction and the reaction quotient. Now, if you remember from about 2 or 3 chapters ago, Q is basically the concentration of the products divided by the concentration of the reactants at any time, all right? So Q is basically the reaction quotient, which represents that ratio, not necessarily in the equilibrium state, all right? Now, R in this case is a molar gas constant, the value of which would be 8.31 times, well, 8.31 joules per mole Kelvin, all right? And T is the temperature in Kelvin. Now, and Q is the reaction quotient, as I said before. Now, if the system were to be at equilibrium, then what that means are two things. One, the delta G value will be equal to 0, as we mentioned before, and the reaction quotient will be equal to K, right? So at equilibrium, delta G is going to be equal to 0, and Q is going to be equal to K. So therefore, we can set 0 here where delta G is, and K here where Q is, and the resulting equation will be this. 0 is equal to delta G standard plus RT ln K. Another way of expressing this is delta G standard is equal to minus RT ln K. So this equation, this final equation gives you the relationship between delta G standard and the equilibrium constant, all right? So just to give you a graphical picture of what we're talking about here, this graph here basically shows you the relationship between the free energy Q and K, all right? Now, Q will be equal to K at equilibrium, but if Q is not equal to K, then the system will not be at equilibrium. And if you remember when we talked about Le Chatelier's principle, the equilibrium will shift so as to change the value of Q so that it becomes equal to K, all right? So what this is showing you here on the x-axis is basically the progress of reaction as you go from reactants to products. The y-axis here is basically the free energy. So what this is showing you here, now this is for a reaction where delta G is negative, which means that the reaction is spontaneous. You start off with the free energy of the reactants here. As the reaction proceeds, the free energy falls until you get to this minimum point here. And then it increases until you get to the, until you get to the free energy of the products, all right? So as you can see here, the free energy of the products is less than the free energy of the reactants, and that's why delta G is less than 0. You'll notice that on this side of the curve, Q is less than K, right? That means that the equilibrium is not reached yet because the reaction quotient is less than the equilibrium constant, all right? But as the reaction progresses, what happens is that the concentration of the reactants will decrease and the concentration of the products will increase. And therefore, what will happen is that the Q value will increase until it gets to the value of K. And that's basically the minimum point here, all right? Which would be the equilibrium position, okay? And then as the reaction proceeds to the products, you see that the free energy increases until you get to that of the products. And at this point here, the Q would be greater than K. Again, from here to here, the system will not be at equilibrium. So this is what happens when you have delta G is less than 0 for a spontaneous reaction. Now, if the reaction is not spontaneous, then what we have here is this graph. And it's basically the same sort of trend that you'll see, with the difference that the equilibrium, well, two differences actually. One difference is that the free energy of the products will be greater than the free energy of the reactants. So that's why delta G is greater than 0. But the other difference is that the equilibrium position here lies further or closer to the reactants, whereas in this case, the equilibrium position is closer to the products, all right? So basically, what we can conclude is that if for a reaction, delta G is less than 0, all right? The standard delta G is less than 0, then at the equilibrium position, the position of the equilibrium would be closer to the products compared to its position relative to the reactants. And the opposite will be true if delta G for the reaction standard is greater than 0. The equilibrium position here will be closer to the reactants, all right? So that's basically a graphical representation of the relationship between free energy and Q and the equilibrium position and equilibrium constant, all right? Okay, so the next thing I want to point out here is this short table, which basically summarizes the relationship between delta G standard and K, all right? So if the system is such that the equilibrium constant is greater than 1 that means, and this is something that you should be familiar with based on your previous algebra experience, ln(k) will be positive or greater than 0, right? If ln(k) is positive, in this equation, that means delta G standard will be negative, right? And therefore, what that means is that the products are favored over the reactants. So in other words, the equilibrium position will be closer to the products compared to its position to the reactants, right? Now, if K is equal to 1, right, if the equilibrium constant is equal to 1, then obviously ln(k) will be 0, which means that based on this equation, delta G standard will be 0, which means that both the products and reactants are equally favored at equilibrium. In fact, I wish I had a graph of this, but if you can imagine a graph of a situation where the products and reactants would be equally, the equilibrium position would be equally close to both the products or reactants. That means that the graph would be such, let me see if I can illustrate something here. The graph would be such that the minimum point would be exactly smack in the middle. Let's say this is halfway the distance. Then the graph would be such that the minimum point would be right there, right? So I don't want to draw the graph, or maybe I should try to draw the graph. If I were to draw the graph, it's going to look very symmetrical like that, right? Where at the very bottom, it's going to be halfway between the reactants and products, which means that both reactants and products, as stated here, would be equally favored. And then finally, if K is greater than 1, again, based on what you know from algebra, ln(k) would be negative, which means that based on this equation, delta G would be positive, which means that in that particular case, at equilibrium, the reactants will be favored over the products, all right? So that's basically a summary of the relationship between the free energy standard and the equilibrium constant. Okay, now what we have learned here has a lot of application. What we have learned in this chapter have a lot of applications in engineering systems and also biological systems. And what I'm showing you here is an application of what we have just learned in terms of free energy and spontaneity of processes and so on. And you may have met this before in your biology courses, because this is basically a very brief summary of what happens when glucose undergoes metabolism to form the product carbon dioxide and water, right? I'm quite sure you're familiar with that particular reaction, which goes through several steps in biological systems, all right? This particular reaction basically provides energy, which converts this molecule, which is known as ADP, and convert it to ATP. And what you should have learned in your biology course is that the ATP molecule basically serves as a quick method of storing and delivering energy, right? And that's because ADP is more stable than ATP. When the ADP molecule is converted to ATP by getting a phosphate group, the resulting ATP molecule is unstable and has energy that it can deliver for different processes, such as the conversion of amino acids to proteins. So just to give you a simple example, we're going to look at this reaction here. Now, these are two amino acids, alanine and glycine. So when they react, they form a dipeptide known as alanyl glycine, right? And it turns out that the standard free energy for that particular process is plus 29 kilojoules. So by virtue of the fact that delta G is positive, we know that this process would be non-spontaneous. In other words, it will not happen by itself, all right? It needs energy in order to overcome the delta G value being equal to plus 29 kilojoules. That energy for that process, because this process can occur, that energy for that process will come from the ATP, right? So as shown in this diagram here, the ATP will basically convert to the ADP, but in doing so, it's going to deliver energy such that this process of making the dipeptide in this case will occur. So basically, this is what happens when you couple this process here with the process of forming the dipeptide. So basically, the ATP is hydrolyzed to form ADP and phosphoric acid, and the energy resulting from that will now favor the formation of alanine, or I should say, drive the formation of alanine, of alanyl glycine from alanine combining with glycine. And when you look at the thermodynamics of this, the delta G value for that process, when this reaction is coupled with the formation of the peptide, you're going to end up with the delta G being negative, right? And of course, if delta G is negative, that means that the process is spontaneous, all right? So that's just one example of how thermodynamics is used to understand, in this case, a biological process, all right? Okay, and that's basically, believe it or not, the end of this chapter. So what that means is we can, let me do this here. We can complete assignment 6. So the next question that we're going to look at is number 4. And there are a couple of parts to number 4. And it says here for number 4, write a balanced equation that depicts the formation of 1 mole of Fe2O3 from its elements. So basically what they're saying is the equation that you're going to write down for this must be such that you only have 1 mole of Fe2O3 solid on the right side. And over here, you're going to have the formula for the elements that make up that compound. So one element that makes up the compound is Fe, iron, and the other element that makes up the compound is oxygen. Now remember, oxygen exists as a diatomic molecule, O2, all right? So the next step in this process is that you have to balance the equation, but the coefficient here for Fe2O3 must be 1, all right? So how would you achieve that? Can anybody tell me how you'd achieve that?
Would you have to use a fraction in front of the O2?
Okay, so what would be the fraction for the O2 that you would use here?
Would it be 3/2?
Exactly, 3/2. And what about the iron here? What's the coefficient here?
2.
Okay, and that's it. That's basically the equation for the formation of 1 mole of the product, which in this case is iron 3 oxide. Okay, we're going to stop here because it's now 10:50, and we're going to continue from here, looking at the other questions. All right, so we'll be resuming at 11. Okay, folks, I'm back. So I have done this part here, which is going to be important for the rest of the question. All right. So this is the equation for the formation of 1 mole of the iron 3 oxide. So the A part is asking, what is the free energy of the formation of 1.00 moles of iron 3 oxide? So let me see if you can take a stab at this. What do you think would be the first step in solving this problem? Anybody? They gave you 1.00 moles of Fe2O3, and they're asking for the free energy, which would be in kilojoules per mole. So what I would do is start off with this and multiply by the appropriate conversion factor. So what do you think the conversion factor is going to be? What would go down here as a denominator? Nobody knows? Come on. Think about it. What number would go down here? And what number, I'm sorry, what number would go down here? And what number would go up here as a numerator? And that's based on this equation. Okay, well, let me help you out some more. Because you have a 1 here, I would put 1 mole of Fe2O3. All right? Now, since I help you out there, what do you think is going to go up here? Okay, so again, let me try to help you out here. You would go to, oh, let me see here. You go to the tables and you would look for the free energy value for iron 3 oxide. Now, the good thing about this is that they arrange the symbols in alphabetical order. So I will look for iron 3 oxide, which is right here. And the value for the free energy for the formation of 1 mole of iron 3 oxide is right here, which is 742.2. So if I go back to I go, 1 minute. If I go back to this, up here, I'm going to put, let me do this here. Come on, come on. Up here as a numerator, I'm going to put minus 742.2 kilojoules. So when I round this off appropriately, it's going to get minus 742 kilojoules, and that would be the answer. So as you can see, that's very simple, all right? Any questions about this one? Any questions? Any questions? Okay, so now that I've helped you with A, let's see what you can do with B. Now, in the case of B, scroll down here, it says, what is the free energy when 454 grams, which is equal to 1 pound, 454 grams of Fe2O3, and they're asking for the free energy in kilojoules per mole. So how would you tackle this?
Do you convert the grams to moles?
Okay, so 454 grams of Fe2O3, you convert to moles, right? So what would be in this conversion factor here? What would go up top and what would go below?
1 mole of Fe2O3 up top.
Okay. And below you're going to have what?
The molecular weight.
Okay, so I did that already. It's 159.69 grams of Fe2O3. All right. So this goes with this. And then what would be the next conversion factor? Because remember, you're trying to find the free energy.
You would do the negative 742.2 kilojoules up top over the 1 mole.
You are correct. And when I did that calculation, I got minus 210 kilojoules. And that's how that is done. All right. Okay, any questions about the B part? Any questions? Okay, so in the case of the C part, I'm sorry, not C part, number 5. Let me get rid of this here and do this and scroll down. Okay, now we're going to leave out the A part because unfortunately the tables I don't think contain the value for PbCl2. So we're going to skip the A part and move on to the, let me see here, hold on 1 minute. Let me check something here quickly, because I think, hold on. Let me see, lead-2 chloride. Yes, okay, so the table does not have lead-2 chloride. It has lead, lead-2 plus, PbO2, PbSO4. Okay, so what I'm going to do is skip the A part since we don't have the value for lead-2 chloride. Now we're going to move on to the B part. And the B part, they gave you this equation, all right? Magnesium plus half oxygen to give you magnesium oxide. So what the question is asking for, by the way, are the values of delta S and delta H of formation. You have to use those values from the tables, and then based on those values, you're going to calculate delta G. Now remember, delta G, the equation that we met today, is that delta G, let me write it here, delta G, oh, you know what, let me scroll up because I'm going to need a space. Okay. Okay, so let me just write it right here. The equation is delta G standard is equal to delta H standard minus T delta S standard. That's the equation we're going to use, right? Now, what we need to do, according to the question, is find delta H standard and delta S standard for the reaction And then we calculate delta G by plugging those numbers into this equation. So when I go to write down the general expression for calculating delta H standard, that would be equal to the enthalpy change of formation of magnesium oxide minus the enthalpy change of formation of magnesium plus that of oxygen, right? However, because we know that magnesium and oxygen are elements uncombined with anything, we know that this is going to be 0 and this is going to be 0. So therefore, all we need to do is look up the enthalpy of formation of MgO. And if I go to the table and look that up, magnesium oxide enthalpy, you're going to see that the value for that is minus 601.70. So going back to this here, I'm just going to say that this would be equal to, oh shoot, let me do this. I'm just going to say that this would be equal to minus 601.70 kilojoules per mole. All right. So at least at this stage, we have determined delta H standard. Let me just draw a line here because what I want to do next is calculate delta S standard, right? And that would be equal to the standard S value for MgO minus the sum of the entropy value standard for magnesium plus the entropy value for oxygen. Now, unlike free energy, these values will not be 0 for the uncombined elements. So we can't assume that we have to look them up. So we go to the table again and look up for the magnesium oxide. And we see here that is equal to, no, that's formation enthalpy. We're looking for entropy. So for entropy, we have 26.94, right, for the magnesium oxide. And for the magnesium, it is 148.65. And then we have to scroll down to see where the oxygen is. And for the oxygen, it is 410. No, I'm sorry, oxygen. What am I doing? 205.14, all right? So those are the values that we'd have to use. So I'm going to go back to here. So I'm just going to put those numbers in. So in the case of magnesium oxide, it is 26.9 kilojoules per mole. I'm sorry, joules per mole Kelvin. You have to be careful with the units. Minus, in the case of magnesium, we saw that is equal to 32.68 joules per mole Kelvin. And then we add to that the entropy standard value of oxygen. But you'll notice in this equation, you have a half here. So you have to multiply that value by a half. And the value for the oxygen is 205.14 joules per mole Kelvin. And then you do your number crunching, which I did. And when I did that, the answer I got is minus 108.3 joules per mole Kelvin. All right. So now that we have delta G standard and we have delta S standard, the only thing is we need to know what the temperature is. And because we know that these are standard conditions, then the standard temperature would be 298 Kelvin. All right. So now we have the three things that we need in order to calculate the delta G. So delta G standard will be equal to delta H, which is minus 601.70 kilojoules per mole Kelvin, minus the temperature, which is 298 Kelvin. And then to that, we're going to multiply the delta S value, which is minus 108.3 joules per mole Kelvin. But there's one other thing we need to take into account. And it's the fact that we have the joule unit here and we have the kilojoule unit here. So we have to do some conversion. In this case, what we're going to do is convert the joule unit to kilojoule over here. So you're going to have 1,000 joules here, 1 kilojoule above, and that will complete this setup right here. And then you do your number crunching, which I did already, I think. Yes, I did. When I did that, the answer I got is minus 569, minus 569, whoops, I'm sorry, minus 5. Let me erase this here. And let me try to make this look a bit more sensible. So the answer I got is minus 569.4, and the units will be kilojoules per mole. So that would be the final answer. All right. Okay, any questions about this one? Any questions?
Yes, I have a question.
Yes, ma'am.
It's kind of hard for me to see the conversion factor for the joules and kilojoules.
You mean right here?
Yeah.
Okay, let me just try to make it more clear above. So what I have down here is 1 kilojoule, whoops, 1 kilojoule divided by 1,000 joules. So that's what's down here.
Okay, and you always want the answer to be in kilojoules per mole?
Yeah, usually delta G and delta H, usually those are expressed in kilojoules per mole, while delta S is usually expressed in joules per mole Kelvin.
Okay, and then I also noticed when you drag down to fill out the delta G, put in the numbers for that. When you originally did the what was it, delta H, you have the unit kilojoules per mole, and then when you put it in, it's kilojoules per mole Kelvin. So is the delta H supposed to have the Kelvin?
Okay, I'm sorry. Where did you see the kilo? You're talking about?
So, yeah, that one that's circled right there.
That's
you don't
kilojoules
have
per
a
mole.
K there. It doesn't have a K there, but when you dragged it over, it has a K now.
Oh, wait a minute. Oh, you mean here?
Yes.
Oh, that's an error on my part. So let me correct that. Thank you for pointing that out. Yeah, there should be no Kelvin there.
Okay, thank you.
Yeah. Okay, any other questions? Any other questions? Okay, so if you understood what I did in this problem for the B part, then you pretty much should be able to do the C part. It's pretty much the same thing. The only difference is that the numbers will be different. All right. So again, you'd have to go to the tables and look up the numbers for ammonia, hydrogen chloride, and ammonium chloride and put them into their respective equations like we did in the B part, and then you calculate delta G based on that. Let me see here. Let me scroll down. I think there's one more. Oh, no, that's it. Okay, so basically for the C part, it's the same process. Different numbers, but the same process. All right. Okay, is it okay for me to clear this? Going once, going twice. All right, let me clear that. Let me get out of that. And let me scroll down to this question. Now, this question, they gave you the equation and they gave you the enthalpy of formation of methanol, which is what the equation is about. And the question is asking for you to calculate delta G standard. So my question to you is, what equation comes to mind when you're solving this problem? The question gives you delta G and it's asking for you to determine the equilibrium constant. And there's an equation that I introduced to you guys, which will help you to solve that problem. What equation relates the free energy standard to the equilibrium constant?
Is it the delta G equals negative RTL and K?
You're absolutely right. So let me just write it up here. It's delta G standard is equal to minus RT, L, and K. In this case, K would be KC, all right? Now, here's where some algebra comes in, and I want to see if you know how to do this. If delta G is equal to all this, then how do we rearrange the equation to solve for K? If delta G standard is equal to minus RT, L, and K, then how do we mathematically rearrange the equation so that we get an expression where we have K on one side and everything else is on the other side? Let me clean this up. So this is K.
Would it be e to the power of delta G standard over negative RT?
Okay, e to the minus delta G standard over what?
RT.
Over RT, very good. So we put in the delta G value, which is given in the question here. So that's minus 166.27 kilojoules per mole, multiplied by T, which is what? 25 degrees, which we have to convert to Kelvin, which would be 298. I'm sorry, not multiply, divide. Man, I'm really messing up today. Okay, so divided by 298 Kelvin, multiplied by R. And remember, R is 8.31 joules per mole Kelvin. And again, here we have a situation where we have joules here and we have kilojoules here. So we need to convert from either joules to kilojoules or vice versa. So here I'm going to put 1,000 joules down here as a numerator and 1 kilojoule up here, so that this unit will cancel out with that unit. The kilojoule units will cancel out, and the mole units will cancel out, and the Kelvin units will cancel out. So there'll be no units in this part of the equation here. So basically all you have to do is put your numbers in the calculator and do the number crunching. And when I did it, the answer I got is 1 times 10 to the 29. 1 times 10 to the 29. And the reason why there's only one sig fig here is because when I worked out all this, I rounded the answer to the correct number of sig figs, which would be 3. And the resulting answer, which I don't have, is expressed to 1 decimal place, which means that when you're finding the exponent of that, the number of sig figs here would be 1. So the answer here becomes 1 times 10 to the 29. All right. Okay, any questions about this one? Any questions?
Wait, can you repeat why it was one significant digit again?
Okay, because I kind of skipped a step. When I worked out all this here, I got an answer which rounds off to 3 sig figs, right? But in the same answer, there's only 1 decimal place, all right? And then after rounding off to 3 sig figs, there's only 1 decimal place. And whenever you're doing this sort of function, e to the whatever the number of decimal places here, the number of sig figs would be here. So this would be 1 sig figs.
Okay, thank you.
All right. So I kind of skipped a step in order to get to the final answer. Okay, any questions or any other questions about this one? Any other questions? Okay, so let me, I guess it's okay for me to clear this, right? Going once, going twice. Okay, let me clear that. Let me do that. Let me scroll down. Okay. Now this question says, consider the formation of NO from its elements, and it gives you the equation right here. And the question says, use the free energy data provided to calculate Kp, all right? So basically what they're saying is, let me go back to my writing function, is you need to find out what Kp is, right? And Kp will be equal to, as we said before, E to the minus delta G standard over RT, right? So what it comes down to, because the question says specifically, use the free energy data, right? So what it comes down to is that you need to find delta G for the reaction and plug it into this equation to find Kp, all right? So how do we find delta G? We go to the tables, right? And we look up the free energy of formation of NO, and we know that because oxygen and nitrogen are free elements, those will be zero. So I did that already. And when I did that, the delta G value I found is equal to 2 times, because you have a 2 here, 2 times 86.55 kilojoules minus 0 plus 0 for both the nitrogen and the oxygen, right? So when I work this out, the answer I got is 173.1 kilojoules per mole, I should add, kilojoules per mole, all right? And then what we do is plug this value into this equation right here. And the result will be this, Kp is equal to E to the minus 173.1 kilojoules per mole divided by R, which is 8.31 joules per mole Kelvin, times the temperature, which again is 25 degrees Celsius, which is 298 Kelvin. And again, as in the previous case, we have to convert the joules to kilojoules. So in this particular case, we're going to put 1,000 joules down here and 1 kilojoules here for this part of the equation. And then we do the number crunching. And when I did that, I got, okay, now in this case, I didn't skip the step that I skipped last time. When I worked out this part here and round off to 3 sig figs, I ended up with minus 69.9 here, right? And because this is 1 decimal place, that means that the final answer must be expressed to 1 sig fig here. And when I did that computation, I got 4 times 10 to the minus 31 as the final answer. And that's how that is done, all right? Okay, any questions about this? Any questions? Any questions? Okay, so that was the A part for number 7, all right? Now for the B part, I'm going to assume that it's okay for me to clear this, all right? So in the case of the B part, they gave you some information here. They gave you the temperature, and they said that delta H for the reaction and delta S for the reaction are nearly constant with temperature. So basically what you're saying is that those values will not change with temperature. We're assuming that. And if that's the case, that means that we can go to the table and determine delta H and delta S for that reaction, for the same reaction that we were looking at here, all right? So they gave you that the temperature is 700 degrees Celsius. And in this case, they're asking for the new Kp value, all right? So they're asking for the same thing, but the delta G will be different because it will be based on the change in the temperature. So what we need to do first is write down the expression which relates delta G, the free energy, to delta H and delta T. So that's delta G standard is equal to delta H standard minus T delta S standard, right? The next step is to find delta H standard for the reaction, which would be, again, products minus reactant. And let me just write the equation here, just to remind you of what the equation is all about, 2NO. So in the case of delta H standard, it's 2 times the value of the enthalpy standard formation of NO, which I've looked up already. I'm going to write it down here. It's 90.25 kilojoules per mole. And for the nitrogen and oxygen, it's going to be 0 and 0. So, and by the way, this should be minus, not plus. Doesn't make a difference, but in this case. So when I work this out, the answer becomes 180.5 kilojoules per mole. All right. And then now in the case of delta S standard, we do the same thing. It's a product minus reactant in terms of those values. And I already looked up the S values for each of these. And this is what I got. 2 times the standard entropy for nitrogen monoxide, which when I looked it up is equal to 210.76 kilojoules. I'm sorry, joules per mole Kelvin. I keep confusing the two. Minus the value for the nitrogen is 191.61 joules per mole Kelvin, plus the value for the oxygen, which is 205.14 joules per mole Kelvin. And when I worked that out, I got 24.77 joules per mole Kelvin, all right? So now that I have the delta S value and I have the delta G value, then I can plug those two values into this expression to calculate delta G, all right? So delta G standard, based on this equation, will be equal to 180.5 kilojoules per mole minus T, which is 700 degrees Celsius. So when we add 273 to that, we get 973 Kelvin. So 973 Kelvin. And then we multiply that by the S that we got here, which is 2 multiplied by 2, 24.77 joules per mole Kelvin. Keep forgetting the Kelvin unit here. Joules per mole Kelvin. And again, we need to convert the joules to kilojoules. So we're going to put 1 kilojoule here, 1,000 joules here. And then we do our number crunching, and I did that already. And the answer I got is 156.4 kilojoules per mole. All right. Okay, so that's basically how we get the B part. Any questions about that part? Any questions?
Are we
Oh,
finished?
no, we're not finished yet. We need to
Okay.
find KP, right? Oh, my bad. Man. Okay, so is it okay for me to clear this because I'm going to need a space? Is it okay for me to clear this?
Yes, sir.
Okay, so let me clear it. So the relationship between KP and delta G, as we said before, can be expressed as K is equal to E to the minus delta G over RT. So we calculated the delta G to be equal to, what was it again? Minus 156.4. No, I'm sorry, positive 156.4. So this is going to be e to the minus 156.4. And this will be kilojoules per mole in terms of the unit. And then we divide that by R, which is 8.31 joules per mole Kelvin, times the temperature, which is again 973 Kelvin. And then we multiply that by, to convert from joules to kilojoules, we multiply that by 1 kilojoule up top, 1000 joules below. And that's all of this down here. And then we do our number crunching. And the answer I got when I worked out this part is minus, hold on, yes, minus 19.3. And this works out to be equal to 4 times 10 to the minus 9. Again, this is 1 decimal place. So this works out to 1/6. And that's basically how that is done. All right. Okay, any questions about the B part? Any questions? Any questions? Okay, so again, you need to submit this. Let me just look at something here before I tell you when. Let me go here. Okay, so this would be assignment number, what is it again? Assignment number
6.
Okay. I'm just creating a Dropbox for you to submit that. Let me see. Okay, so today is the 24th. So I would say by the 26th at midnight, it's due. Let me just make sure that the Dropbox is open. It is. So now you can submit assignment number 6 in the appropriate Dropbox in Canvas. All right. Okay, so that's when that's due. It's due Wednesday. All right. Okay. So any questions about this chapter before I move on to the next chapter? Any questions? All right, so let me go back to the files folder. Oh, you know what? Let me clear this first. And then go to, let me close this. Let me go to lecture notes. Okay, so the next topic we're going to talk about here, and I'm going to publish the PowerPoint for that right now, is electrochemistry. All right, so let me download this. And, okay, what's going on here? Oh, okay. So as the name suggests, electrochemistry, this is where we're going to look at the relationship between an electric current being either made by a chemical reaction or produced by a chemical reaction, or on the other hand, using an electric current to drive a chemical reaction, right? So those are basically the two halves of this particular topic that we'll be looking at, all right? Now, before we actually get into the actual topic of electrochemistry itself, we need to remind ourselves of what we mean by redox reactions, all right? Redox is the abbreviation for reduction oxidation. So before we get into that, as I said before, this slide here is showing basically what happens in electrochemical processes. There are two types. One where energy is released in the form of electricity by a spontaneous reaction, and then the other type is where electrical energy is used to drive a non-spontaneous reaction, right? And we'll be looking at both of them, both of those types of processes in this chapter. But we need to remind ourselves of the term redox and what redox means, and more specifically, what reduction means and what oxidation means, right? So this is something you should have met in General Chemistry 1, if I'm not mistaken, chapter, is it 3 or 4? I don't remember, whichever chapter that deals with solution reactions, aqueous solution reactions, all right? So if we look at a simple example of a redox reaction, such as what we have here, you'll see that magnesium is said to undergo oxidation because as far as the magnesium is concerned, going from left to right, the magnesium atoms are losing electrons to form magnesium ions, right? So this is oxidation, right? Oxidation is the loss of electrons. And then the oxygen, as you go from left to right of this equation, is gaining the electrons lost by magnesium to form the oxide ions, right? So therefore, that's reduction where electrons are gained, right? So basically, oxidation takes place when a particular atom loses electrons, and reduction takes place when an atom gains electrons. And if you were in my General Chemistry 1 class before, you would have been introduced to this memory aid, oil rig. This helps you to remember what is what in terms of redox reactions. This stands for oxidation involves loss of electrons, reduction involves gain of electrons, all right? So hopefully that would help you to remember what is involved in both oxidation and reduction. And I should also add that in every redox reaction, you always have the transfer of electrons. Something is losing electrons, and those electrons will be transferred to something else, right? And another thing I need to mention, which will become important, and this is something you should have met before actually, is that the number of electrons lost in the oxidation process must always be equal to the number of electrons gained in the reduction process, all right? So you won't have any situation where these two numbers here, the numbers of electrons transferred, will be different. The number of electrons lost in oxidation must be equal to the number of electrons gained in the reduction. Okay, so next thing I'm going to talk about here, again, is something that you should have met before, and that would be the rules concerning redox reactions, or I should say, I'm sorry, concerning oxidation numbers, right? Or oxidation states, as they say in some textbooks, right? So what do we mean by this term, oxidation number, oxidation state? Well, you should have learned that this is basically the charge that an atom would have in a molecule or in an ionic compound if the electrons were completely transferred. Now we know that in a molecule, you don't have the complete transference of electrons. But if you can imagine that occurring from the less electronegative atom to the more electronegative atom of the compound where the bonds are formed, then you can imagine ions being formed, and basically the charge on those hypothetical ions will be equal to the oxidation number. And there are some rules concerning determining the oxidation number of different elements in different circumstances. And again, this is something you should have met before. So I'm just going to go through this rather quickly. The first rule is that any element not combined with any other element, in other words, it's free by itself, that automatically is assigned an oxidation number of 0, right? So some examples are shown here, right? Sodium, beryllium, potassium, even the diatomics like hydrogen and oxygen, or a polyatomic like phosphorus. In all these cases, the oxidation numbers are assumed to be equal to 0, all right? Because these elements are not combined with other elements. Now, if you're dealing with ions, monatomic ions specifically, the oxidation number is equal to the charge on the ion. So some examples are shown here, like lithium, the lithium ion, which has a +1 charge, that would also be the oxidation number, or the iron 3 ion, which has a +3 charge, +3 would be the oxidation number, or even in the case of an ion such as oxide, where there's a -2 charge, the oxidation number of oxygen in that case would be -2. The third rule is specific for oxygen. And what this rule says is that the oxidation number of oxygen is usually -2, but there are certain exceptions. And the exceptions would be the oxygen in hydrogen peroxide or oxygen in any compound which contains a peroxide ion. In those cases, the oxidation number of oxygen in those compounds would be -1. Excuse me. All right. So in the case of this third rule here, as I said before, it's specific for oxygen. If the oxygen is combined with any other element, you can assume it's -2, excepting where we have the peroxide ion present, or if we're dealing with hydrogen peroxide, in which case the oxidation number of oxygen in those compounds will be -1. Okay, so that's rule number 3. Rule number 4 is another specific rule, this time specific to hydrogen. And according to this rule, hydrogen has an oxidation number of +1, excepting in cases where the hydrogen is bonded to a metal. In those cases, the oxidation number of hydrogen is -1, all right? So if hydrogen is bonded to pretty much any other compound or any other element, I should say, you can assume the oxidation number is +1, but if it is bonded to a metal, then the oxidation number of hydrogen in those circumstances will be -1. Okay, and then we get to rule number 5, which says that, and this is kind of specific for group 1A metals, group 2A metals, and fluorine. So, and I should add a short phrase here, so let me do that now. So according to this rule, hold on. According to this rule, group 1A metals, the oxidation number is +1. Group 2A metals, the oxidation number is +2. And fluorine, its oxidation number is always -1 when these elements are bonded to other elements, all right? So basically, if these elements are combined with other elements, then basically we can assume that for group 1A metals, the oxidation number of the metals in those compounds will be +1. For group 2A metals, the oxidation number of the metals in those compounds will be +2. And if fluorine is bonded to any other element, its oxidation number is always -1, all right? Okay, so that's rule number 5. Then we get to rule number 6. Now, rule number 6 basically exploits what we have just learned in terms of the previous 5 rules, because what this rule says is that the sum of the oxidation numbers of all atoms in a molecule or ion is equal to the charge on the molecule or ion. Now, this rule is useful because you can use it to determine the oxidation number of other elements that were not described in the previous 5 rules, right? So basically what this is saying is that if you have an ion such as the carbonate ion, right? The sum of the oxidation numbers of hydrogen, carbon, and the 3 oxygens in this ion will be equal to the charge, which is -1 in this case. So basically you can exploit this rule to answer this question, which says, what are the oxidation numbers of all the atoms in the hydrogen carbonate ion? Well, we know that based on the previous rules, that the oxidation number of oxygen is -2, and the oxidation number of hydrogen is +1. So we do not know directly from the previous rules what the oxidation number of carbon is, but we do know, based on rule number 6, that the sum of the oxidation numbers of hydrogen, carbon, and the 3 oxygens here must be equal to -1. So what we can do is basically set up an equation where we take 3 times the oxidation number of oxygen, which is -2, add it to 1 for the hydrogen, and then we basically have an unknown here, which would be the oxidation number of carbon. But when we add them all up, we're going to get -1. So therefore, we can easily solve for the unknown. And it turns out that in this case, the unknown, which is the oxidation number of carbon, turns out to be equal to +4. All right, so that's basically how we can determine the oxidation number of pretty much any element in a molecule or an ion. As long as you know what the formula is, then basically you can use these rules to determine the oxidation numbers of the different atoms in it. Okay, we're going to stop again, take another break, and resume at 12 o'clock. All right?
Real quick, I just want to ask, are we going to have these rules given to us?
No, you're not going to have these rules. But you see, the thing is that if you practice these rules enough, eventually you'll know them. You don't even need to memorize these rules word for word. But if you practice, determining the oxidation numbers of, elements in a compound, then you should have no problem. All right? Okay, so let me take my break now before you ask me another question, and then we'll get back. If you have any questions, you can ask me on the other side of this break. All right? Okay, folks, I am back. So let me ask you before I start, are there any questions concerning what we just covered?
I don't have a question concerning that, but I was wondering if you were able to check your email about the test.
I did reply, well, I checked my email just before class started, and I did reply to one from, hold on. I did reply to one from,
No, you said you had to check your email about a prior obligation on Thursday.
yeah, but okay, who is this I'm talking to?
McCoy.
Oh, McCoy. No, I haven't been, I forgot to do that actually, check that email. Let me see if I can do that quickly right now.
Okay. Because I'm just wondering what I'm supposed to do if you're not available, because the only day that I'm available is Thursday
Yeah.
afternoon.
Because I have something to do on Thursday. I don't remember the time, that's the only thing. So let me see here. Oh, okay. I guess I can do it because this thing I have to do is at 9:15 and it will take about maybe 45 minutes. So to answer your question, I would say I'll be available after, I should be available after 10 o'clock.
Okay, well, my lab class is from 2 until whenever we get finished with lab, which is normally anywhere around 4 o'clock. So I would
Okay,
say
yeah.
probably like 4:30 just to be safe.
Yeah, I should be available.
Okay, would that
Just
be in
in
your
case,
office?
yeah, you can come to my office. Just in case,
Okay.
however, give me a call before just to make sure that
On Skype?
Skype, or you can leave a message on my voicemail.
Okay.
All right.
And what am I
Okay.
supposed to do if you happen to not be available?
I don't know yet, to be perfectly
Okay.
honest. I mean, right now as it is, I don't see a problem, but sometimes,
Okay.
you know, things happen.
Okay, I'll call you then when I get done with
yeah,
lab.
right, exactly.
Okay,
Okay.
thank you.
Yeah, no problem. Okay, so any other questions before I move on? Any other questions? Okay, so another thing I want to talk about, which is something you should have met in Chem 1, is how do you go about balancing redox equations? But before you do that, there's one thing I need to mention, which unfortunately I don't have any slides to talk about. In fact, you know what? Let me get out of this here and go to my writing application here. Come on. Okay, so you remember the equation I showed you earlier, which is Mg plus O2 to give MgO, right? And to balance this, we're going to need a 2 here and a 2 here. Okay, now, remember we said that we can define redox in terms of gain and loss of electrons, right? But we can also define redox in terms of increase or decrease in the oxidation number of a particular element. So in those terms, oxidation would involve an increase in oxidation number, and reduction will involve a decrease in oxidation number, right? So applying that to this equation here, the oxidation number of magnesium is 0 on that side. On this side, it's +2. So basically, you have an increase going from 0 to +2. So that would be oxidation as far as the magnesium is concerned. On the other hand, in the case of oxygen, oxygen has an oxidation number of 0 on the left side, but here it's going to be -2. So that would be a decrease in oxidation number from 0 to -2 for oxygen. So that means that oxygen is undergoing reduction. All right. So that's just another way of determining what is being oxidized and what is being reduced. So, and this does not in any way conflict with what we said before concerning electrons being lost or gained. So these are just two different ways of looking at redox reactions. So I thought I should just mention that. And now I'm going to go back to the PowerPoint here. And we're going to now talk about something, as I said before, which you should have covered in Chem 1, and that is how do we balance redox equations, all right? So the best way to learn this is to go through the steps using an actual example, all right? So what we're going to look at is the reaction where the iron 2 plus ion is being oxidized by this ion, which is called the dichromate ion. Now, admittedly, there's a piece of information that's missing here, which I'm going to add right now because it would be unfair for you to just try to figure out what the other product is. So let me include that here. So I should have, let me just add right here. Also producing the chromium 3 plus ion. All right. So that's one of the products of this reaction. Now, with that said, let's proceed to solve this problem. So the first step in balancing a redox equation is that you have to figure out what the unbalanced equation is. Now, in some cases, you may be given the unbalanced equation, in which case that means that step 1 would have been done for you already. But in the case of the example that we're looking at here, we have to look at the information provided and we have to determine what are the reactants and what would be the products. So based on the information provided, you can see that the Fe2 plus and the dichromate ions would be the reactants. So they would be on the left side. Then you put your arrow in, pointing to the right, and then you write down the products of the reaction, which would be the Fe3 plus and the chromium 3 plus on the right side. So this would be the unbalanced equation for the reaction. So that leads us now to step number 2, which says that you need to separate this equation into 2 half equations, right? So one half equation would represent the oxidation on the other, and the other half equation would represent the reduction. So in this particular case, one half equation would be going from Fe2 plus to Fe3 plus. That's the oxidation half equation. And then the reduction half equation would be the half equation where you start with the dichromate on the left, and you're going to end up with the chromium 3 plus on the right, okay? So that's basically how you separate the unbalanced equation into 2 half equations. Then the next step is where we balance all atoms other than hydrogen and oxygen. So that's step number 3, right? So basically this balancing that you're going to do is pretty much in the same way that you would balance any other equation, but this only applies to the all atoms excepting oxygen and hydrogen. Now, in the case of the first half equation, you have one ion on both sides, so you don't need to add anything to that one. But in the case of the second half equation, you have 2 chromium atoms represented on the left, and you have one only represented here on the right. So that means that to balance the chromiums, we need to put a 2 here in front of the chromium 3 plus on the right. So therefore, the result will be that half equation, all right? So for step number 3, what we're concerned with is simply balancing all other atoms excepting oxygen and hydrogen, all right? Now, we will be balancing the oxygen and hydrogens in the next step, step number 4. So for step number 4, it says for reactions in acid, what we do in order to balance the oxygens is that we add water molecules to the side that is deficient in oxygen, and we add enough of them so that we end up with a balance of oxygen. Also, what we need to do next is balance the hydrogens by adding H plus ions to the side that is deficient of hydrogens, and we add enough in order to achieve the balance of the hydrogens, all right? Now, again, in the case of the, let me go back here. In the case of this equation here, there are no oxygens, no hydrogens, so therefore we do not need to make any changes to that half equation. However, for this half equation, you'll notice that there are 7 oxygen atoms here on the left, and there are none on the right. So we need to balance the oxygens. And as I said before, the way we do that is that we balance the oxygens by adding water to the side, which is deficient of oxygens. And in this case, we would add 7 water molecules to the right side, all right? So by adding 7 water molecules to the right side, we're adding 7 oxygen atoms, which balances with the 7 oxygen atoms on the left side. Now we need to concern ourselves with balancing the hydrogens. Now you'll notice that there's a total of 14 hydrogen atoms on the right side, and there's none on the left side. So what we need to do, according to step number 4, is that we need to add 14 hydrogen ions to the left side to basically balance the 14 hydrogens on the right side. All right, so that's step number 4. So just to recap, for step number 4, we balance the oxygens by adding water to the side that needs the oxygens to balance the oxygens on the other side. And we balance the hydrogens by adding hydrogen ions to the side which is deficient of hydrogens so as to achieve the balance with the hydrogens on the other side. Okay, now the next step is where a lot of students tend to make errors, all right? So I'm going to try to explain this as slowly as possible so that you understand how to do this step. Now, in addition to balancing all the atoms in both half equations, we need to also make sure that the charges are balanced. In other words, the total sum of charges on the left side of the equation, or for both half equations, must be the same on the right side of each half equation, all right? So let's see how we achieve that in the case of this half equation here. Now, previously, we just had this Fe2 plus going to Fe3 plus. So basically the charges here are not balanced because you have a +2 here, you have a +3 here, right? So in order to balance the charges, as stated here in rule number 5, what we need to do is add electrons to one side of each half equation so as to achieve the balance. Now you might be wondering, which side do you add electrons? And basically you add the electrons to the side with the higher net charge, all right? So if you look at this half equation here, the net charge on the left side is +2, the net charge on the right side is +3. So that means that you're going to add your electrons to the right side, which has a net charge of +3. So the next question is, how many electrons would you add? Well, you add enough so that the total charge on this side would be equal to the total charge on this side, in which case, in this case, you only add 1 electron in this case, right? So when you add 1 electron here, you're going to get a total of 3 minus 1, which is +2, which balances with the +2 on the left side, all right? So that's how you balance this half equation. Now, what about the next half equation? If you look at the next half equation, which is this one right here, the total number of charges on the left side here would be 14 plus charges minus 2. So therefore, let me go to my pen function here. So therefore, in this case here, the total charge on this side would be +12. And then when you look at the right side, you have 2 times +3, which is +6, and there's nothing as far as the water is concerned in terms of charges. So the total charge on this side is +6. So in this case now, you have to ask yourself the questions, to which side would you add the electrons and how many would you add to that side? And as I said before, you add to the side with the higher net charge. So since you have +12 here and you have +6 here, you would add your electrons to this side here. So basically, the next question you have to ask yourself is how many electrons? And in this case, you would add 6 electrons to the left side, because by adding 6 electrons to the left side, you're adding 6 negative charges, which will reduce the total charge on the left side from +12 to +6, which balances with the +6 on the right side. So therefore, the equation resulting from that, the half equation resulting from that, would be this right here, all right? So just to recap, just to make sure that you understand what's happening here, whenever you're balancing the charges, you need to add electrons, and the side to which you add electrons will be the side with the higher net charge, right? Then you add enough of those electrons to that side so that the total charge resulting will be equal to the charge on the other side, and therefore your charges will be balanced. All right? So that's step number 5. Okay. Any questions so far? Any questions before I move on to step number 6? Any questions? Okay. Step number 6. Very important. And it goes to something I mentioned before. If you remember, I said that in any redox reaction, the number of electrons lost and gained must be the same. Now you'll notice up to this point here, step 5, the number of electrons lost in the oxidation reaction is 1. The number of electrons gained here in the reduction reaction or half reaction is 6, all right? So obviously the number of electrons are not equal. So this begs the question, how do we get the number of electrons lost in the oxidation half reaction equal to the number of electrons gained in the reduction half reaction? Well, the answer is that you'd have to multiply one or both equations by certain integers so as to equalize the number of electrons lost and gained. In this particular case, all we need to do is multiply this half equation here by 6. So let me do this here. You multiply this half equation here by 6, because by doing that, you're multiplying this by 6, but you have to multiply everything by 6 in that half equation, right? So once you get the 6 electrons here, that would be equal to the 6 electrons here. So the result of multiplying that first half equation right through by 6 will be, whoops, what did I do? Will be that right there, all right? So that's what you need to do in order to equalize the number of electrons lost and gained. Now, let me just say that in some instances, you may need to multiply both equations by integers. In fact, we're going to look at some examples of that shortly, all right? But in this case, we only need to multiply the first half equation by the appropriate integer, which is going to be 6, all right? And the second half equation, we can leave it as it is. So once we do that, then the next step, which is step number, oh, that's the second half equation right there. Okay, the next step is that we add both half equations together. Now, whenever you're doing addition of any two equations, even half equations, you have to ensure that you cancel out those items that are common to both sides, right? So that's what we're going to do here. We're going to add this half equation, the oxidation half equation, to the reduction half equation, all right? And the first thing that we'll notice, of course, is that as a consequence of what we did in step number 6, we have 6 electrons on the left in the case of the reduction half equation, and 6 electrons on the right in the case of the oxidation half equation. So when we add these two together, we can cancel the 6 electrons out, all right? And there's nothing else to cancel out. So basically, we'll be left with this as your net equation for the reduction, or for the redox reaction between the dichromate iron and the iron 2+ ion, all right? Now, what I normally suggest to my students at this stage, because this should be the final answer, but just to make sure that this is correct, what I suggest to my students always is that they do a final check through to make sure that everything is balanced. All the atoms are balanced for each element on both sides, and also the charges are balanced. In other words, the total charges on the left will be equal to the total charges on the right. So we have to do some verification here. So let's do that right now. In the case of the hydrogens, we have 14 hydrogens on the left side, and we have 14 hydrogens on the right side. So the hydrogens are okay. We have 2 chromiums on the left side and 2 chromiums on the right side. So that is okay. We have 7 oxygens total on the left side, and we have 7 oxygens total on the right side. And here we have 6 ions on the left total, 6 ions on the right. So basically all the atoms are balanced, but we also have to confirm that the charges are balanced. In other words, when you add up the total charges on the left, it should be equal to the sum of all the charges on the right. And these calculations here basically prove that that's the case. So the 14 hydrogens will be 14 times 1, minus 2 from the dichromate. And then we add 6 times 2 for the iron 2+. We add that up, we get 24. And then we multiply on the right side for the iron, 6 times plus 3. That gives you 18. And then 2 times 3, that gives you 6. 18 plus 6 gives you 24. So now the charges are balanced, all right? So that's basically how we do the balancing of redox equations. Okay, any questions about this before I move on? Any questions? Any questions? Any questions? Okay, so the next thing I want to talk about is, well, let me just mention first that all that we have done so far is in regards to redox reactions taking place in an acidic medium, right? So as you can see here, for example, we have H+ here, but we can also have redox reactions occurring in a basic medium. And to get the equation for that particular type of redox reaction, we just basically need to add a couple more steps to what we just did here, right? So in order for us to get the redox reaction or redox equation for a basic environment, what we need to do is add hydroxide ions to both sides for every hydrogen ion that appears in the final equation, which is this equation right here. And then once we do that, then we're going to basically form water molecules, which will cancel out. And I'm going to show you how to do that right now. So let me get out of this right here and go to my writing application here. Let me get rid of this. So what I'm going to do now is write down the equation, the last equation that I obtained as a result of balancing the initial unbalanced redox reaction. So that equation is 14 hydrogen ions plus the dichromate ion plus 6 Fe2 plus. And then on the right side, I'm going to have 6 Fe3 plus plus 2 chromium 3 plus 7 water molecules, all right? So this is what we ended up with based on all the steps that we followed previously. Now, this is in the acidic medium, all right? So how do we get from the acidic to the basic? As I showed you before, what the instruction says in step number 9 is that whatever the number of hydrogen ions that we have here in the equation, we add an equal number of hydroxide ions to both sides. So what that means is that we add 14 hydroxide ions to this side, and we add 14 hydroxide ions to the other side, all right? Whatever the number of hydroxide ions that we add to one side, we have to do the same to the other side. Now, the key thing you need to recognize here is that each time a hydroxide ion is added to a hydrogen ion, you're going to have the formation of a water molecule, right? So the result of adding 14 hydroxide ions to the 14 hydrogen ions will result in the formation of 14 water molecules, all right? So now that we have 14 water molecules on the left side, then you'll notice that we have 7 water molecules on the right side. So what can happen is that these 7 water molecules will cancel out 7 of the 14 water molecules on the left side, and then the net equation resulting will be 7 water molecules plus the dichromate ion plus the 6 iron 2 plus ion to form 6 Fe3 plus 2 Cr3 plus 14 hydroxide ions. And that would be it. That would be the balanced equation under basic conditions, all right? So that's basically how you can go from the equation for the reaction in the acidic medium to the equation for the reaction in the basic medium, all right? Okay, any questions about this? Any questions? Any questions? Okay, so just to make sure that you understand what we were doing, we're just going to look at some examples and let's see if you can go through the steps with very little help from yours truly. So let me get rid of this here. And I'm just going to make up some reactions. I can't even promise that these reactions will actually occur in reality, but you know, this is a useful exercise in terms of the steps involved in balancing a redox reaction or redox equation. So let's say you're given what should I put here? SO2, okay. So let's say you're given that unbalanced equation and you're asked to balance it according to the steps I went through before, all right? Okay, so what would be the very first step in this process?
create two half equations?
I'm sorry?
Would we split it into the half equations?
Yeah, your volume is kind of low for some reason. I don't know why, but I think I made out what you said. You're saying that I should separate into two half equations, right? So that would be one half equation, and this would be the other half equation. Okay, very good. What's the next step? I'm sorry, SO2, not SO3, SO2. Okay, what would be the next step?
Is it balance everything except oxygen?
Balance everything except oxygen and
Hydrogen.
hydrogen, exactly. So what does that mean for the first half equation?
Put a 2 in front of NO3.
With a 2 in front of the NO3, very good. What about the second half equation?
You would leave it as it is.
Exactly, very good. Okay, so now that we have done that, what would be the next step?
Add electrons.
I'm sorry?
Do we add electrons?
Nope. You're jumping the gun. You're jumping like how many steps you're jumping? You're jumping you're jumping one step.
Oh, we add the H2O. In
Okay,
the,
so you're talking about balancing the oxygens, right?
yes.
So how would you balance the oxygens for the first half equation? In other words, to which side would you add the water molecules and how many?
You would add 3 H2O to the left side.
You sure? Let me give you a little hint here.
Oh, you would add 6 H2O.
There you go. Okay. What about the second half equation? To which side would you add water molecules and how many would you add?
You would add 2 H2O to the right side.
Okay, I agree with you. Okay, very good. All right, so far we have balanced all the atoms. So the next step would be what?
Add the H pluses to the opposite side to balance them.
Okay, so what does that mean for the first half equation?
Add 12 H plus to the right side.
Okay, very good. And what about the second half equation?
Add 4 H plus to the left side.
Very good. All right, what's the next step?
Now we balance the electrons.
Now we balance the charges by
Adding
Oh.
electrons.
adding electrons. Okay, so again, let me warn you, especially for students learning this for the first time, they tend to screw up at this stage, right? And the biggest mistake I've noticed over the years is that they tend to add electrons to the wrong side. All right. And they also tend to add the incorrect number of electrons in some cases. All right. So let's see if we can do this without screwing it up. All right. So how would you balance the charges for the first half equation? In other words, to which side would you add electrons and how many electrons would you add?
Would it be add 10 to the right?
Very good. 10 to the right. So you're going to add 10 electrons. And for those of you who don't get it, the reason why you had 10 electrons here, because previously, before you add the electrons, the total charge here would be plus 12. and the total charge on the right to be 0. So if you want to, I'm sorry, not plus 12, plus 10, because that's 12 minus 2, that's plus 10, right? And you have 0 on this side. So to get the plus 10 reduced to 0, we add electrons, and we add 10 electrons. So that gives you an addition of 10 negative charges, and that works out to be 0, which balances with a 0 on the left side. Okay, very good. Let's deal with the second half equation. Again, the question is, how many electrons would you add, and to which side would you add the electrons?
You add 2 to the left side.
Okay, very good. You add 2 electrons to the left side. And again, to explain the reason why, before you add the 2 electrons here, you had 4 plus minus 2, so the total charge here is plus 2. Here you have 0. So therefore, to get the charges balanced, you need to add 2 electrons here, because by adding 2 electrons, you're adding 2 negative charges, which works out to be 0. All right? Again, achieving the charge balance. Okay, very good. Okay, so let me do some erasure here, because I've created a mess in explaining all this stuff. So let me just erase that. Let me erase this. This. Okay. So now that we have balanced all the atoms and the charges, what would be the next step?
Multiply by a common factor to get the E negatives to be equal.
To get the electrons
Yeah.
to be equal, right? So remember, and this is true for all redox reactions, the total number of electrons lost must be equal to the total number of electrons gained. As it is right now, that's not the case. So as, who was that who said that? I don't remember. I didn't.
Me.
Oh, Megan. Okay, as Megan said, you need to multiply each of them by a particular integer so that the number of electrons lost and gained will be equalized. What that means in this case is that we'd have to multiply this equation here right through by 5 so that we convert these 2 electrons into 10 electrons. So when we multiply right through by 5, you're going to end up with 10 electrons here, 5 times 4, 20 hydrogen ions here, plus 5 sulfate ions. And then you're going to get 5 SO2 plus 10 water molecules. All right. So, oh shoot, let me make this more neat. This here should be 5. So this should be 5 right here. Okay. Okay, so what's the next step?
Cancel out any common factors.
Okay. In other words, you'll be adding this equation to this equation, right? So what I'm going to do is cross out this one to avoid confusion. All right. So as, okay, who was the person? I'd like to give credit to whoever said what they said. Who said that? Who said that a while ago?
To cancel?
Yeah. Oh, that was you, Miss McCoy?
Yes, ma'am. Yes, sir.
Okay. Yeah, I'm not a man. So anyway.
Sorry.
So 10 electrons cancel out here and here. And then what else? Okay. These 6 water molecules here will cancel out 6 of these, leaving behind 4. And these 12 hydrogen ions here will cancel out 12 of these, leaving behind 8, right? And then we add what remains. So what do we have remaining? Well, on the left side, we have 1 nitrogen molecule reacting with 8 hydrogen ions plus 5 sulfate ions. And then on the product side, you're going to have 2 nitrate ions plus 5 sulfur dioxide molecules plus 4 water molecules. And that should be the final answer for the reaction in an acidic medium. But, and I'm going to reiterate again, as I said, say to my students all the time, make sure that everything is balanced at this stage, including the charges. So let's do that now. We have 2 nitrogens here on the left, and that balances with the 2 nitrogen on the right. We have 8 hydrogens here on the left, and that balances with the 4 times 2, 8 hydrogens on the right. We have 5 sulfur atoms on the left, 5 sulfur atoms on the right. And then in terms of the oxygens, we have 5 times 4, 20 oxygens on the left. And on the right, we have 2 times 3, 6. 6 plus 5 times 2, 10. That's 16. And then 16 plus 4, 20. So the oxygens are balanced. And then as far as the charges are concerned, we have 8 minus charge, minus 10, because 5 times minus 2 gives you minus 10. So the total charge here will be on minus 2 on the left. And on the right side, we have a total of minus 2 from the 2 nitrates here. There are no charges for the others. So the charges are balanced as well. And that's it. So that would be the answer for the equation for the reaction under acidic conditions. Okay, very good. Now, the next question I have to ask you is this. What if you're asked to determine the equation for the reaction under basic conditions? So what would be the next step in order to achieve that?
Would you add 8 OH negative to the left side?
Well, you would actually add 8 hydroxide ions to both sides.
Yeah.
Remember, whatever you do to one side, you have to do to the other side. All right? So what happens as a result of this right here?
8 water.
8 water molecules will be produced. Exactly. And then what will happen next? Let me erase the top part here since I'm going to need a space. Let me erase the top part here. Okay, so as a result of what I just did, right, the formation of 8 water molecules here, what will happen next?
The 4 water molecules on the right will cancel out 4 of the 8 water
Okay,
molecules
so-
on your left.
Okay, very good. So these 4 water molecules will cancel out 4 of these. So the final answer will be N2 plus 4 H2O plus 5 SO4 2 minus. So that's the left side. And then on the right side, you're going to have 2 NO3 minus plus 5 SO2 plus 8 hydroxide ions. And that's the final answer under basic conditions. So let me put basic here and acidic here. All right. And that's how that is done. Okay, any questions about this? Any questions about this example? Okay. So is it okay for me to clear this? Going once? Going twice? Okay, so let me do that. And what I'm going to do now is another example, just to make sure that you guys have a firm grasp of what is involved, the steps involved, and what happens at each step. Okay, again, I'm just going to make up something. Again, this does not necessarily mean that this reaction is going to actually occur in practice. So let's say you have MnO4 minus reacting with let's see here, with NO2 minus to form Mn2 plus NO3 minus. Okay, so let's say you're given that and you're asked to balance this. So what would be the first step?
equations?
I'm sorry?
Do we make the half equations?
Okay, so one half equation would be this. And the other half equation would be this. Okay, what would be the next step?
Balance them based on everything except O and H.
Okay, so balance all other atoms, all atoms excepting hydrogen and oxygen. Well, what that means in this case is that there's no change because there's one manganese here, one manganese here, one nitrogen here, one nitrogen here, so you don't need to make any changes as far as that is concerned. So what would be the next step?
Add H2O to balance the oxygen.
Okay, so what does that mean for the first half equation?
Add 4 H2O to the right side.
Add 4 water molecules to the right side. And what does that mean for the second half equation?
Add 1 H2O to the left side.
Add 1 water molecule to the left side. Very good. Okay, what's the next step?
Add H plus to balance the hydrogen.
Okay, so what does that mean for the first half equation?
Add 8 H plus to the left.
Okay, so we add 8 hydrogen ions to the left. What about the second half equation?
Add 2 to the right.
2 hydrogen ions to the right. Okay, very good. Next step.
Electrons.
Okay, so what does that mean for the first half equation? How many electrons would you add? And which side? To which side would you add it?
You would add 5 to the left.
Okay, you'd add 5 electrons to the left. And for those of you who don't understand the reason why, before you add the 5 electrons, you have a total of 8 plus charges minus 1, so a total of plus 7 on the left side. And on the right side, you have a total of plus 2. So in order to reduce the plus 7 to plus 2, you have to add 5 negative charges. That's the reason why you add 5 electrons to the left side. Okay, what about the second half equation? To which side would you add the electrons and how many?
2 electrons to the right.
2 electrons to the right. I would agree with that because before you add the electrons, the state of affairs was that you have minus 1 here and you have 2 minus 1 that gives you plus 1. So to reduce this to minus 1, you would have to add 2 negative charges. So that gives you a total of minus 1, which balances with a minus 1 on the left side. Very good. Pretty good, actually, because usually when students are introduced to this for the first time, they usually screw up this part, but you guys have been doing well so far. Okay, so let me erase this here. Okay, so now that we have balanced everything, atoms and charges, what's the next step?
I had a quick question about this
Yeah.
part.
Uh-huh.
So I know that the electrons have to cancel. Would you ever do a situation where you would use a fraction, or would you just multiply the top by 2 and multiply the bottom equation by 5?
That's exactly what you would do, what you just said.
Okay.
Multiply the top by 2 and the bottom by 5. All right, so that's the next step, actually. So I would multiply this by 2, everything throughout by 2. So that gives you 10 electrons here, plus 16 hydrogen ions, plus 2 MnO4 minus, to give 2 Mn2 plus 8 water molecules. And then I'll multiply this equation here by 5 right throughout. And the result of that would be 5 water molecules plus 5 NO2 minus to give 5 NO3 minus plus 10 H plus 10 electrons. All right. Okay, so now that we have done that, what would be the next step?
cancel stuff out.
Okay, so what will cancel out?
The electron, the E negative,
Okay, always the electrons will cancel out completely. All right. What next? What will cancel out? Or what else would cancel out?
the 16H plus would become 6H plus because the 10.
Okay, so the 10 here of the hydrogen ions on the left side will cancel out 10 of the 16 on the right side. So you're going to end up with 6 here. Okay, very good. What else?
Do the same with the H2O and it'll be 3 on the right.
Okay, so these 5 water molecules will cancel out 5 of these, leaving behind 3. And therefore, what we do is just add what is left. And you're going to end up with 6H plus 2 MnO4 minus plus 5 nitrite ion. So that's on the left. And then on the right side, you're going to have 2 Mn2 plus, whoops, 2 plus 3 water molecules plus 5 nitrate ions. And then what do we do at this stage?
Check the answer.
Well, check to make sure what?
It balances the charges and the
And the atoms, right?
molecules. Yeah.
So let's do that. We have 6 hydrogens here, and we have 3 times 2, 6 hydrogens on the right side, so that's okay. We have 2 manganese here, 2 manganese here, so that's okay. We have 5 nitrogens here, 5 nitrogens here, so that's okay. And then as far as oxygens are concerned, we have 2 times 4, 8, 8 plus 5 times 2, 10, so that's 18 on the left side. And then on the right side, we have 3 oxygens plus 5 times 3, 15 plus 3, 18. So the oxygens are balanced. And then as far as the charges are concerned, on the left side, we have plus 6 for the hydrogens, minus 2 for the 2 permanganetes, and then minus 5. So that gives you what? 6 minus 2, that's 4 minus 5. So that's minus 1 on this side. And then on the right side, we have 2 times plus 2, which is plus 4, 5 times minus 1, so that's minus 5. So that's equal to minus 1. So the charges are balanced. So everything is balanced, all right? Okay, so as we said before, this is what happens in the acidic medium. So how do we get, whoops, I'm sorry. How do we get from acidic to basic if you're asked for the equation in the basic environment?
You add 6 hydroxides to each side.
Right? 6 hydroxide ions added to both sides. And what's going to happen here?
So that'll become 6 water molecules.
Exactly, 6 water molecules. And then what happens next? Let me create a space up top here to write down the final answer. Okay, so what happens next?
The 3 water molecules on the other side will cancel out, and the one on the left will become 3 H2O.
Okay. And then we write down the result, which would be 3 H2O plus 2 MnO4 minus plus 5 NO2 minus to give 2 Mn2 plus 6 OH minus plus 5 NO3 minus. And that would be the answer for the reaction under basic conditions. All right, okay. So if you can master this, then you should be able to answer questions from the assignment. In fact, let me go here. Let me close this. Then we go to assignments. So this would be assignment number 7. Let me see here. Okay, so this is assignment number 7. And as you can see, the first question is similar to what we have been doing. Of course, they specify whether or not the reaction is being done in acidic or basic medium. So you have to take that into account. In fact, for the rest of the time here, I guess we can start looking at these questions. Let me just check something here before I get started with these. Okay, so there's a lot of redox balancing, and then there's some other things which you'd have to look at based on what is covered in the rest of the chapter. Okay, so let me scroll back up. I'm just going to choose, oh, you know what? It's 12:50. So let me take another break, and then we get back here at 1 o'clock, and then we can just look at maybe just one of these questions here. All right.
Can you publish the assignment so we can print it out?
Yes, ma'am. Let me do that right now, actually. So it is now published. Okay, so let's take another break because I need to stretch my legs, and then we'll resume at 12, and then we'll call it a day. Okay, folks, I am back yet again. So as I said, what I will do is one more problem of that type from the assignment, if I can find it. Let me close these out here to avoid confusion. Okay, so which one shall I do from the first question? They're like what, A through F? Let me see, I'm just going to choose an arbitrary one. Eeny, meeny, miny, mo. Okay, let me choose this one here. So, in fact, let me rewrite it. Do I have enough space for this? Let me see here. Maybe I can fit this in. Let's see. All right, so let me go to my writing thing here. All right, so let's do this one together. So what would be the first step, folks? Hello, anybody there? What will be the first step? Come on, guys. We did 2 examples of this before, so this should be easier now.
We're supposed to split it up, right?
Uh-huh.
I don't really know how you would do that. Based on-
All right, let me help you out here. So the 2 half equations, since you have only one reactant here, which contains pretty much, some of the elements of the products, I would start off with HXeO4 minus for both half reactions. XeO4 minus. In the case of the first half reaction, the product would be XeO6 4 minus, and in the case of the second half reaction would be Xe, which by the way is xenon. All right. So that would be how I would split them up. Okay, what's the next step?
It would be to balance Xe, but it already is.
Right, okay, very good. So that's true for both of them, right? Okay, so what would be the step after that?
Balance the oxygens,
By?
adding H2O to a certain side.
Okay, so how many water molecules would you add to this first half equation, and how many, and to which side?
You would add 2 to the left.
Okay, so add 2 water molecules on the left side. What about the other half equation?
You would add 4 to the right.
4 water molecules to the right. Okay, very good. And then what will be the next step?
You would have to balance the H pluses.
Balance the hydrogens by adding H pluses. Okay. So what does that mean for the first half equation?
Do we include the H that's attached
mean-
to the,
Yep.
so it would be 5 to the right?
Okay, so 5 hydrogen ions on the right side. What about the second half equation?
It would be 7 to the left.
Very good. What next?
I'm sorry, can I ask how we got that?
Okay,
I'm a little
because you
confused on
have
that part.
8 hydrogens here, and you have 1 here. So to balance the hydrogens, you need 7 more hydrogens in the form of H plus on the left. Got that?
Yes, and then the first one, how did you get 5?
Okay, because you have 4 here plus 1. So that's 5 on the left, which means you're going to need 5 on the right. All right. Okay, what next?
Balance the electrons or add them, I
Oh.
guess.
Okay, so we need to balance the charges by adding electrons. Okay, so what does that mean for the first half equation?
You would add 2 to the right side.
You'd add 2 to the right because over here you have a -1 total. Over here you have 5 minus 4 as +1. So yes, you need to add 2 electrons here because by doing that, you're reducing the charge from +1 to -1. Okay, very good. What about the second half equation? To which side would you add electrons and how many?
6 to the left.
Add 6 electrons to the left. Okay, and the reason why is because before you add the 6 electrons, that would be a total of 7 minus 1, which would be +6 on the left, and you have none on the right. So yes, you need to add 6 electrons to reduce the charge here on the left to 0 from +6. Okay, so what's the next step? Let me just clean up some of this here.
Multiply the top equation by 3.
Multiply the entire top equation by 3. You're absolutely correct, my dear. So you multiply this by 3. So the result of that would be 6H2O plus 3HXeO4 minus to give, excuse me, 3XeO6 minus plus 15 hydrogen ions plus 6 electrons. Okay, so basically what we need to do now is add these 2 equations together. So what would be the result of that? What will cancel out?
The electrons cancel out.
Electrons will cancel out. What else?
The 6H2O would become 2H2O, and the other one cancels out.
Okay, so these 4 will cancel out 4 of these, leaving behind 2. What else?
The hydrogens.
The hydrogen
So-
ions, right?
Right. So
These
then
7
Correct.
will cancel out 7 of these, leaving behind what? 8, right?
Mm-hmm.
And that's it. So we simply need to write down what is left. You're going to have 2H2O. And then these 2 will be added to give you a total of 4HXeO4 minus. And then on the right side, you're going to have xenon plus 3Xe O6 4 minus plus 8H plus. And then we need to make sure that everything is balanced. We have 2 oxygens here plus 16 oxygens, so that's 18 oxygens on the left, and 3 times 6, 18 oxygens on the right. We have a total of 4 plus 4, 8 hydrogens on the left, 8 hydrogen ions on the right. We have 4 xenons here, 3 plus 1, 4 xenons. And as far as the charges are concerned, we have 4 negative charges here. And we have 3 times -4, so that's what, -12. -12 plus 8, that gives -4, so the charges are balanced. Now remember, the question says specifically that you need to write the equation for what happens in a basic solution. So what does that mean for the next step?
You add hydroxide ions to each side. In this case, it would be 8.
Okay, so add 8 hydroxide ions to both sides. So what does that mean for this right here?
That becomes 8 waters, but then it becomes 6 because you can cancel out the 2 on the
Okay,
other
so these
side.
2 water molecules, we cancel out with 2 of those, leaving behind 6. So the final answer, I'm just going to squeeze right in here, will be 4HXeO4 EO4 minus plus, oh, I forgot to put 6 here, plus 6 OH minus to form XE plus 3XE O6 4 minus plus 6 water molecules. And that will be the final answer, all right? And the only other thing I want to add is that there's a special name given to a redox reaction where there's only one reactant involved. And that term is called disproportionation. 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 Oh, that's it, right. So that's a special type of redox reaction where there's only one reactant involved, which is the case here. All right, we're going to stop here for now. What I'm going to do is, in fact, before I forget, let me do that right now. I'm going to publish the video for the rest of that chapter. Let me see if I can do that here. Oh, it's already published, right? So basically what we have done so far, we have basically covered the first 4 videos of that chapter that I've posted in the modules. So you have the responsibility of watching the other videos. If you have any questions, if there's anything that you don't understand, please feel free to contact me. Even though I don't have office hours tomorrow, but I can make myself available. If I should be able to, because I don't have anything pressing tomorrow to do except grading papers. So make sure that you watch these videos and contact me if you have any questions, all right? Preferably through Skype, okay? All right, so unless there are any questions, before I forget, I'm sorry?
I was just gonna ask a quick question about the problem.
About what problem?
The one on the screen.
Oh, okay, quickly.
Yeah, so when you're adding the 8 HOs, you don't need to add 8 to the other side because you crossed out the 2, right?
Oh, shoot, you're right. Hold on, this should be 8 here.
Okay.
Okay, my bad. My bad. So this should be plus, hold on. Thank you for that. So this should be plus 8 OH minus, which means that this should be also 8 OH minus. All right, so please make a note of that. Okay, any other questions quickly before I go?
Do you want us to work on these by ourselves, or are we going to continue working on them next class?
Try to work on them by yourselves. I think by now you guys should be able to work on them, and then we can discuss any areas of difficulty or whatever. And then we'll go to the other topics in that chapter. All right. Okay, so that's it, folks. I'll see you guys on Wednesday. All right, so